Good morning and welcome to all of you on the last day of Faculty Development Program on the topic Recent Advances in Renewable Energy Technologies. Today our speaker is Dr. Sunil Singh Kushwaha. He has already joined us. Good morning, sir.
Yeah, good morning. Yeah.
So before he start the session, I would like to give brief introduction about him. Dr. Sunil Singh Kushwaha is Principal Scientist, Council of Scientific and Industrial Research, National Physical Laboratory, CSIR, NPL, Delhi. He has done MSc in Physics from Banaras Hindu Vishwavidyalaya, Varanasi, MTech in Solid State Materials from IIT Delhi. He has been awarded PhD in Physics from National University of Singapore. He has also done postdoc from NUS Singapore. He has more than 85 publications in various peer-reviewed and indexed journals, conference proceedings, and book chapters. He has been awarded for Early Career Research Award from SERB DST India in 2018. He is life member of Meteorological Society of India, MSI India, Material Research Society India, and Indian Physics Association India. Dr. Kushwaha research expertise includes growth and characterization of various 2D materials, topological insulators, thin films, epitaxial 3 nitride layers, and heterostructures. Characterization techniques includes HREED, AFM, STM, HRXRD, PL, and Raman spectroscopy. Today he is going to speak about hydrogen generation towards green energy application. We are honored to have you today with us, sir. So now I will hand over the session to Dr. Sunil Singh Kushwaha. Sir, you can start now.
Okay. So, thank you for your kind introduction and good morning to all. So, I just wanted to share the slide. Hello. Uh, my slides are visible.
Yes, sir, it's visible.
Okay. Yeah. Sorry. So, yeah. So, first of all, I would like to thank Professor Thakur and Professor Nidhi and Dr. Priti for the kind invitation. So today I am going to talk about this hydrogen generation towards green energy application. So just to brief overview where NPL. So basically this is our NPL located near this IRI Pusa. It is in New Delhi. And our main mandate, of course, we are doing the research, but also we are taking care of this NMI of India, means National Meteorology Institute of India. So of course we have this 7 SI units, and then we are moving doing this conventional SI but now we are moving toward the quantum based SI units. For example, previously we have this length or kg measure with this platinum iridium rod or platinum iridium 1 kg mass, but now we are moving towards this realization through the Planck constant. So that is just overview of our institute, basically what we are doing. And of course, in the field of energy, we are having the very large area clean room where we have this very means primary solar cell metrology for this calibrating the solar cell. So basically, when people talking about the efficiency, like our efficiency is 20%, 15%, then how anybody can believe? So for that one, we have set up the very large facility, even in collaboration with PTB Germany, and it is also located in our clean room inside the NPL. So this is just related to energy we are doing, and of course, a few groups we are working on the material science for making the different application. So I will just briefly give some of the example why we are interested in this green hydrogen energy, and of course there is various approaches to uh, this generate the hydrogen, and then which technique is good and what is the limitation, and then I will take some of the example because being I am basically working on this nanomaterials and 2D materials. Of course, I will show some of the examples related to our own research. Like we have fabricated this MOS2 and PTSE2, that is the well-known two-dimensional materials. And then, of course, we will consider this others material like topological and even for this third nitride semiconductor. Then I will just describe some summary on future where we have to move toward this energy generation. So I think today is last day of the lecture. So of course, most of the faculty and participant, they are aware of energy. But just to begin with this one, of course, we can see these forms of energy. It is like everywhere. Even if I am talking, you are listening, you are doing. This is also energy, because without energy we can't do. But of course, it depends how much requirement we need or what is the impact on the environment, and then accordingly we have to also select the form of the energy. So if we see the form of energy, it's a lot. Like if you name anything, is there like light energy, thermal energy, electrical energy, solar energy, nuclear energy, this biomass energy, geothermal energy, and then of course wind energy, hydroelectric energy, heat energy. So all are there. So of course, again, if we this divide into the two sectors, like one is like energy related to like non-renewable energy sources. So non-renewable energy sources means, of course, when we putting whatever the materials, and if it is not, we are not able to get again back, it is the non-renewable energy sources. So for example, one of the example we know, all know that, like coal, natural gases, oil, biomass. So this kind of thing, once we destroy, for example, oil or coal, then of course we are not gaining. And another energy sources, that is the renewable energy sources. So that is like solar. We have the amendment of this solar from our sun, and we are very lucky that most of the, like at least if throughout the year we are getting at least the sunlight minimum 8 to 10 hours. So that is the advantage to move toward this solar energy in India, and also of course it is spreading a lot. And if you see from 2014 and onwards, it is increasing several folds. So of course, other renewable energy sources like wind, tidal. So all also we have this facility when we have this ocean area or some area that is also people started to use this kind of energy sources. So, of course, we have to, as a scientist and as a academician, we have to see all the statistical data, means where we are going and how much we required, and then what is the percentage, and how we know that which one is better and which is not better, and so this kind of thing. This is one of the this graph it is showing from this International Energy Agency in one this World Energy Outlook in 2023. So they already projected that it is going to be consumed around 30 terawatt by 2050. So that is the one of the this required, that of course we can't rely on only one kind of the sources. Of course we have to mix, or we have to do the different, and also it depends on the what sources is available with us. So if we see, of course, even if you can see this liquids, so liquids is still showing like increasing. It is even from 90 we use this like 5 terawatt per year, and still if you see in 2038 it is showing some incremental, maybe 5 to 6%. But if you see the coal, again coal have a lot of the uh, this increasing. But of course, this renewable sources, if you started in the 90, of course it was very less. But of course we can see it is also moving towards means getting the more participation in this energy resources. Now, of course, nuclear is there, and then natural gases. So all we have to see which kind of the energy required, and then accordingly we have to move. And then of course we have to find out which method or which material or which technology is better for our in future. So of course, when we see this non-renewable energy sources, as I say, this basically um, presently we are, especially the researchers in field of energy, they are of course struggling with this. Uh, that is one of the things that natural resources is limited, and of course our population or our demands, it is increasing day by day. And then another is like this we can see this temperature are increasing, or maybe you can see this global warming kind of thing. For example, this winter we have just maybe 5 to 10 days only this cold was there. Otherwise, again we are feeling means almost there is no cold in even Delhi in January now. So that is the one of the effect we are facing, and of course we have to move towards how we are going to reduce this kind of global environment changing or increasing the earth temperature. So then of course when we see that we can use the different energy sources, and if we see the data, of course this oil, gas and coal is still very high, like 24%, 23%, 38%. Of course this kind of things we have to move to this renewable energy source at 9%. And in future, if we can separate this thing, even renewable energy sources up to at least 20-30%, then of course we have the most of the things we can solve the problem. So, so of course, this we have to find out the different way, different sources, and of course, it is not like only in India, but it is the problem of the worldwide. And then one thing is that this everybody are looking for this sustainable development for this renewable energy sources. And then according to, of course, they have the policy for this international agency that by 2021, that is they say net zero policy. So it means we have this carbon dioxide emission and other things will be minimized. So that's again we don't want to use more of the energy sources related to our like fossil fuels. That is also of course significantly contributing to our environmental pollution and climate change. So one of the things is of course solar energy harness from the sun's. Okay, it is in abundant and renewable power is available. So when we are talking about this renewable energy sources, we can see different renewable sources is like, of course, this hydropower energy, wind energy, geothermal energy, solar energy, and then biomass energy. So of course, out of this one, we can see If we combine like solar energy and then abundant presence of this water on the earth, basically, if you see the ocean or this one, of course, and then if we can make some kind of it to make it combination of this one, so that is the one technology comes in the picture, that is even now started, some of the vehicle also started with this using the hydrogen. So this hydrogen production, if we can do by solar driven water splitting process, that is the efficient way to solve the scarcity of fossil fuels and overcome the environmental degradation situation by zero carbon emission. So, so basically, of course, it has some good things that of course we can do, but how we are going to do and what is the procedure and why we need the hydrogen only. So we have to just see the this one uh, means as a part of the renewable energy source. So this hydrogen production from this renewable energy sources is most viable replacement for fossil fuels in the future, owing to its escalated efficiency. So hydrogen fuel has advantage over natural gasoline, such as non-toxic because it is non-toxic, inexpensive, higher energy density. Means it is high energy to weight ratio. So of course, when we want to gases or something, that at least it don't have too much mass. Otherwise, if conversion and then of course transportation and all other things will be also one of the issue. So so in this case, if you compare with this gasoline, diesel, natural gas, and hydrogen, we can see this is a specific energy of hydrogen is almost 2 times higher than the other fuels. So that's the reason hydrogen is selected as a highly efficient and can be used for transportation, storage, and power replacement in the places where other energy sources are difficult or expensive to access. So of course, if we even if this hydrogen again react with the environment or combustion only, then it generate again water. So why it is that is the reason this hydrogen is particularly appealing. So of course, when it is side product or waste product is again water. So it is not like we have again some kind of the you know, global or warming or maybe this kind of the earth temperature increase or some kind of thing we can reduce. So thing is, of course, how we are going to generate this hydrogen. So of course, there is a different way that we can make it this water. We can split in the process where this water is split into hydrogen and oxygen molecules. So there are various process of water splitting that is include this photocatalytic, electrochemical, thermochemical, radiolysis, photobiological, and photoelectrochemical. So of course we can see like whatever the process we have, of course that is product is only H2 and O2. That is the product, and then we can see this different way like what process is required. For example, if we do electrolysis of water, then we have to flow this electric current. In case of thermochemical, we have to use very high temperature. For biological, of course, we have to use bacteria enzyme. So this is the a different approach. So of course, this is again it requires some other energy sources. But when we are coming to this photoelectrochemical and photocatalytic, we can again have this photon. So it means we have the energy sources. So of course, we can use this again the solar energy, or even we can have this use the sunlight. So when we see like when people started, okay, of course, different depends on the if we are not in India, for example, in some Greenland or some other places where this there is no sunlight, not too much sunlight. Of course, they have other approaches. That is, for example, they have started this thermochemical water splitting process where they use this very high temperature around this uh, almost three this 2000 degrees Celsius. And then of course after that they make this water, and then water is split here, and then after it can become this fuel cell. So of course there is some approach, of course we can heat, but again if we are heating in India or in some industry where already we have this warm weather condition and all other, this is the not feasible because it requires very high temperature, around 2000 degrees Celsius. So that's the reason this kind of a reactor is not good, especially in our country. So, but I will just show means what is the different approaches to generate the hydrogen. So another is like this is the very starting, or even when we started the electrochemistry, that is this electrocatalytic water splitting. So this is the very one of the innovative approach that people use. This of course when you have this electrolyte like water there, and then they put the membrane, and then they have the two cathode and anode. The simple things, just they put the positive, this connect with the current, and then of course we can see this hydrogen generate, and then due to membrane, oxygen will go, for example, here toward this anode, and hydrogen will go toward the cathode. That is the one of the approach, and it is the very well technique. So that is the region, of course, it has been started, and so this is the basic of the PEC or photocatalytic. So of course when we see here again we are applying the current, and this again this current, or sorry, whatever the power we are applying, this is again coming from our this indirectly, or something from the coal or some kind of thing. So we wanted to reduce, or we wanted to minimize this kind of the sources. So of course that is the reason we have to use this photon energy or solar cell. So here it is like a photocatalytic water splitting process happen. That is in case, of course, we are not going to use the very much dependent on the electricity, but we can use this light energy. So that is, of course, typically if we see it is from the sun only. So this is to drive this chemical reaction that is split this water into hydrogen and oxygen. So this process is carried out using a photocatalyst, which is for example, this nanoparticles or nanopowder films that absorb light and facilitate the water splitting process. So again, of course, this there will be two kind of the reaction occurs, whether it is electrocatalytic or photocatalytic. That is the reduction reaction. So reduction reaction generally consider at the cathodic side where this reduction occurs, the electrons reduce the proton, that is hydrogen plus, from water to form the hydrogen gases. And another reaction is oxidation process, because it is the parallel process. If you have the reduction reaction, then another part it will be the oxidation reaction. So at the anodic side where this oxidation occurs, the whole oxidized water to form the oxygen gas and protons. So in both cases, of course, one channel is to get the hydrogen, or another channel to get the oxygen. Of course, we have the more interest to get the hydrogen, because hydrogen, as I saw, it has this very two times specific energy is higher than other gases. So of course, we can use for the fuel cell, and of course, oxygen is required for our daily usage of plants and all other things. Of course, this is not the like means there is no carbon emission or carbon dioxide emission during the process. So of course, in this limitation is like in the photocatalytic water splitting process, the separation of generated hydrogen and oxygen is required immediately, which will consume additional energy. That is the causing this low efficiency of the water splitting process. So of course, we can use this gas separator to make it like water and sorry, to separate this hydrogen and oxygen. But of course, there is different approach. So one approach is like we can use this photoelectrochemical process. That is we call this PEC water splitting. So if we see this PEC, water splitting, this hydrogen is produced from the water using sunlight and specialized semiconductors called these photoelectrochemical materials, which use light energy to directly dissociate water molecules into hydrogen and oxygen. This is the one of the things sometimes we can PEC, or this one we also say the artificial photosynthesis process. Why we say so? For example, this normal photosynthesis process for the plants. For example, we are having this light here and plant is there. We are producing CO2 and H2O. Then of course, when this light is absorbing, we can have this sugar plus oxygen. Same with this one. We have this water is here, and then we putting the light here, and then from here we are getting the product is H2 plus O2. So this is the we call this artificial photosynthesis process as well for the PEC process. So of course, when we see how PEC works or how it works, so of course, uh, first of the all, we want this some kind of semiconductor materials, because semiconductor materials have the of course different band gap, and then it will absorb the light which excite this electron hole pairs. Then other process is the charge separation, because once we have this electron hole pairs, then how we are going to separate this electron hole pairs, and then because it will move toward the photocathode or leaving a hole behind. And then third process is hydrogen and oxygen production. So this when we have this electron and hole pair separated, then electrons and holes move to the surface of the photocatalyst, where they produce hydrogen and oxygen molecules. So of course again it depends whether on the cathode it will be this hydrogen, and for the anode it is the oxygen. So it depends on the reduction and oxidation process. So when we go more details, we can see like this is the one of the setup where of course we have this three cells. So basically one is like a cathode, one is anode, and then another is like some kind of the reference electrode, because when we are measuring the voltage, of course if we don't have the reference electrode, because due to this chemical process or corrosion process, we don't know exactly how much voltage. So that's when we put this AG cell reference electrode. And then here for the lab basis or most of the things, we use this solar simulated sunlight. That is the 1.5 am, that is equivalent to 100 milliwatt per centimeter square, this power energy density of the light. So again, it is the same process. Like for example, when we have this photons and then photoelectrode, then of course this will generate like electron and hole pair. Then this hole will react or make it like oxygen evolution reaction with the H2O, then it will make the oxygen plus 2H plus, and then this 2H plus one will react with this electron, that is the hydrogen evolution reaction, then we will get this hydrogen gas. So basically we have the two process, like we can get this oxygen, and then another process simultaneously we are getting the hydrogen. So of course, when we are seeing this being a semiconductor materials, we can see, of course, we have the different semiconductor, like two types of the semiconductor. One is like N type, and another is P type. So how we know where this oxygen evolution or hydrogen evolution reaction place? That is depend on the type of the semiconductor materials used for the electrode. So if we have this N type semiconductor, then this oxygen evolution reaction will take place at our photoanode, that is we call the photoanode, and hydrogen evolution reaction takes place at the platinum electrode. In case of P type of the semiconductor, of course it is vice versa. Like here we have this counter electrode like platinum, we have this oxygen evolution reaction, and then this on the photocathode, because now it is P type, so it will not the photon, but basically the photocathode. That is means here we have this kind of hydrogen evolution reaction take place. So, and of course, when you have this biphotoelectrode PEC system in which we have this both N and P type semiconductor, then of course we can replace this platinum, and then we put N and P type, and then according to what is the mobility and what is the this band gap and carrier concentration, accordingly one electrode work as a hydrogen evolution reaction, another electrode will work as a oxygen evolution reaction. So one of the important parameter is that for this PEC water splitting, when we see this reaction need, this net gives a free energy of 238 kilojoule per mole. So it means if you consider with this band gap in terms of energy, it should be 1.23 electron volt. So it means whatever the semiconductor materials, at least their band gap should be in range of 1.23 electron volt or above that one, because that's the reason it will drive to water splitting reaction. Because of course when we can generate hydrogen and using the various materials, but also it depends on how much this band gap is falling, or especially like conduction band edge and valence band edge, how much they are falling in this H2, H2, H2 and O2, H2O2. See the difference is 1.23 electron volt. So when we see most of the materials like semiconductors, materials, especially like 2D materials, we can see all materials are there. Like for example, silicon carbide, bismuth cellulite, MOH2, zinc oxide, TiO2. So, so one of the starting material was this TiO2. When we have this photo PEC water splitting by Fujisuma and Honda, and of course, when we see this band gap is around 3.2 electron volts. But I will come to the some of the example when we are talking this TiO2. So now, as because once we evolving this, how we are going to change or add more advantage of this solar cell or this sunlight. Then one of the approach is like instead of using any electric power supply, we can use this solar panel to connect with this electrode and cathode to the solar panel, and then this will give you the or this hydrogen generation. So here, of course, we are tapping more solar light or sunlight, because one is sunlight is from this solar cell, and another light we are putting here in our electrode system. Means whatever we have this photocathode or photoanode. So that reason we are tapping solar light 2 times here. So of course, advantage like it has a very high efficiency, and here we are reducing our means putting less using this conventional current, because all are the solar based current. So then this that is we call this photovoltaic photoelectrochemical cells. So so we can see this PV PEC system even can achieve higher overall efficiency compared to traditional PEC system, even without having any other extra source. Then another approach, of course, as I mentioned, when we are developing the new materials, then always we think about to make something more or something, whatever the materials present, we can use this one. So one of the material that is people use this dye sensitized PEC water splitting cell, where they use this dye sensitized materials. I will not go in more details, just I am giving some example. Then of course, like we have the solar cell, like tandem solar cell, then here also they have put this tandem cell PEC water splitting process. So again it is have like different photocathode, photoanode, and then it is connected with the all consist of multiple semiconductor layers stacked vertically, and each layer has a different band gap designed to absorb a specific portion of the solar spectrum. So of course, when we see when of course the sunlight is coming, and then it is considering from 200 to 1100 nanometer on the earth. So of course, if we have this material that can absorb most of the spectrum, then it will be good. So that is the reason People use these multiple semiconductor layers to having that getting the more absorption of the sunlight, and then of course more electron hole pair will generate, and then accordingly more this hydrogen generation will be happen. So of course so and then of course if we have this another factor that is called this built-in potential. When we have the different semiconductor materials, then they automatically they have the, due to the different in the band gap, it will make this built-in electric potential will be uh, achieved within the layer, and that will help to enhance this charge separation and then reducing this recombination losses. Because as I mentioned previously that when we have this hydrogen and electron and hole pairs are generating, so that is not only thing is generating, but how we are going to transport. And before that, it should not recombine electron and a hole pair again. Otherwise, again it will convert it to back to the proton. So that's the one thing is the transportation, like electrons will move toward this one electrode, hole will go another electrode, and another part is that they have to not combine to make again this photon. So that's the reason we have this some of the materials or some of the process which require this to reduce this recombination losses to get the higher efficiency of the PC water splitting. So of course, when we see this perovskite based material, also people have used. Just I will skip this one. This is just to show means what kind of materials people have used. So this is the one of the basically materials design, and then this is also called this house system design, and people have designed the very well system that is called this PEC thermoelectric hybrid system. So in this case, the two system work in tandem, where the electrical output from the thermoelectric system can be used to power the PEC process, and that is potentially increases its efficiency. And again, vice versa, waste heat from the PEC reaction can be captured and utilized to maintain the thermoelectric materials at an optimum temperature, enhancing their performance. So basically, this is the chain process. For example, this is our solar light. Then there have the materials. Of course, this heat captures like waste heat energy. Then this thermoelectric devices. So here we can produce the electricity, and that can be used for our water splitting process. And then during the water splitting process, whatever the uh, high or heated hydrogen or oxygen is coming, then again we can use this kind of waste heat energy for the thermoelectric. Because thermoelectric case, of course, we need some temperature difference between two materials or at the high temperature. So that is the one of the, of course, this is the one approach. Of course, if we, when we see, it looks very nice, but when we can design, then it take a lot of time. So of course, it have the very much advantage, like you have the increased efficiency by capturing and utilizing waste heat. These hybrid systems can improve overall energy conversion efficiency compared to standard PC system. And of course, this is the one of the utilization of multiple energy sources. You are using the thermoelectric, you are using the solar energy. So all the systems means it is, and finally you are getting the green hydrogen energy. So that is the multiple energy sources involved in this process. So overall, if we considering like between photocatalytic PEC and PB, of course, PC process, as I mentioned, that we generally use these bulk materials or nano powders, and then here we have, of course, hydrogen oxygen generation is there, but separation is not there. So we don't know means separating again. You need required more sources or more approach. In case of the PEC, of course, these have the two different electrodes are there, and then accordingly, as per the electrode, hydrogen and oxygen will move toward this counter electrodes, and then there will be not a problem with the separation of the hydrogen and oxygen. And of course, when we have the PV, of course, we have the double advantage, like using the sunlight, not only on the photoelectrode, but also we can use this sunlight to generate the energy here. So, of course, when we see cost wise or some process wise, of course, efficiency wise, uh, PC have the low efficiency, but PV is required still little bit high cost, because again we are using the solar panel. But of course, with due time, or maybe after few years, maybe cost will be again the similar, and then people will move from this now conventional PEC to the PV PEC. That is the one of our future area where people can use this kind of techniques to increase this high efficiency. So, when we have this, it is not like only we have this materials requirement is one of the difficult tasks. Like, so first of the materials, that is the study materials, should have band gap of 1.23 electron volt, which is the thermodynamic requirement for this hydrogen generation. And of course, this when we go inside or going in the more details of the system or more details of the materials, you can see this proper conduction band and valence band edge position relative to this water redox and oxidation potential is one of the important parameters. So again, it depends on the whether it is N type or P type semiconductor. Then accordingly, uh, you can select the materials, and then you accordingly this HER and OER can place at the different electrode. So of course, we can select the semiconductor materials, but one of the most parameters and most things is like we have to select the semiconductor material that is should be cost effective, earth abundant elements or large scale implementation. Because when we are doing it at the lab scale, of course we need very small material, but of course when the production is required, we need some kind of these materials that have the earth abundant in the nature. So of course, other thing is like we have to see this what is the electrolyte we are using, like pH value, and then all this electrolyte resistance, particle size and defect, shape and size of the nanostructure. So all factors consider. So so there is, of course, there is very need for the struggling or to getting the more some efficient, stable, robust semiconductor materials. And of course, it should be not like we have this toxic materials or something like this, because when you have this toxic material, of course, it will again pollute the environment. So that is the all combination we have to see. It is not like only efficiency is important, but also we have to see this what is the side product or what is the toxicity level of the system. And most of the thing, because we are putting this materials or semiconductor materials in our this electrolytes. So basically it is the chemical process, so we have to also see whether it is stable inside this electrolyte or not, because it is not like you put material and it has very high efficiency, but after 30 minutes, after 1 hour, after few days, if it is not working, then again it is a lot of loss of the resources. So of course stability is one of the parameter as well. So as I mentioned, when we started this water splitting, especially this photoelectrochemical water splitting process, that is started by this Honda and Fujishima in 1972, and they have selected the TiO2, one of the materials that is used for this PC water splitting. And of course, after that, people have started with the TiO2 with the different materials. But the problem is like TiO2 is the uh, when we see this band gap of the TiO2, it is like 3.2 electron volt. That is considering only UV light. So it means when we are this light is falling on this TiO2 based material, then of course it is only taking 4% of our solar spectrum. So that is the reason to enhance this PEC efficiency, different approaches have been followed, and even TiO2 this materials like different doping, surface passivation, ion implantation, and band gap engineering um, to enhance this PEC efficiency of our this TiO2 based nanostructures. So of course, this is some kind of literature. I will just not go in more details. Yeah. So another thing is, it is of course with the time when we started in the lab, of course we can use the any substrate, any materials, and then we can see okay what is the efficiency. But when we are seeing in the real approach, our means how we are going to put our this for the commercial application, then it requires some kind of devices which have the flexible in nature. So flexible in nature is not only means solve your problem, but also it will reduce this transportation cost, or even this for example, when you have these solar panels, like 100 centimeter by 100 centimeter, or for example 5 meter by 5 meter, of course you can transport. But some of the area, if you have large thing, then of course it is very high transportation charge will be there. So in this case, if we have this flexible things, for example, at home we have this aluminum foil, for example 1 meter roll or 2 meter roll, 3 meter roll, but it is just coming in your handbag, or maybe some like a small jute bag, you can bring that one. So this kind of the approach always required. And then of course there we started with this different solar cell. Sorry. Solar materials. And then one of the approach, like they have this polyvinyl and all other this like materials are polymer based materials to make the roll by roll devices. So of course it is very good when we are dealing with this organic semiconductors which require very low temperature or room temperature process. But what happens when we have the some materials, some of the semiconductor, it is not possible to grow at room temperature. Or if you are doing some physical vapor deposition techniques, then it requires very high temperature. So one of the approach is we can use this different metal foils. So of course metal foils like thin metal foil, as I mentioned, even like aluminum foil, titanium foil, moly foil, all of the things we can use. So approach is, of course, these metals fire have this good thermal and electrical conductivity. So even the backside conductivity, if you want, or something contact you want, no need to deposit any other materials. Already this back contact will be your metal foils. Another thing is uh, when we have this high temperature growth process, like sometimes, for example, we have this gallium nitride or some other materials, RMOs2, this required 600, 700 degrees Celsius. So that process, this polymer based substrate, PET substrate, can't be used for the this kind of the application. So that is the one approach. Of course, we have this thin metal foil, and then application like we can see this. For example, this is the model they have proposed. Like you have this photoelectrochemical cell here, then your sunlight is here, solar panel is here, flexible, and then you have this flexible thing. So accordingly, you can move it, roll it, and then you can use. And then also another approach, flexible, is not only transportation but also sun angle is also not like only falling perpendicular every time. It depends on the what is the time in the day. In the, for example, 12 o'clock it will be the like center, but in the evening it will be like some different direction. So that's reason if you have this various coating all over the vehicle or something, then you can get this sunlight efficiently. So I will just take some of the example like we also do in our lab to make this different materials. Like we started with, for example, the same thing like TiO2, and then we have grown this TiO2 on the titanium metal foil. That is again the flexible foil. Then we have the simple electrochemical anodization process, and then after that we get this TiO2 nanotube wires, and then we get some kind of the 2D materials. As I mentioned, it requires like 600 to 700 degrees Celsius process when we are growing some MOS2, and then we have coated this one. So of course, we can't use the substrate which have this very low temperature processes like polymer and other things. So that's the reason we have selected this metal foils. So this is the, for example, after grow, we have to characterize our systems with the different techniques. So like this is our SCM images. So from here, we can see this formation of this TiO2 nanotubes. And then when we measure the what is the diameter of the TiO2 nanotube, this is coming around 200 to 250 nanometer. And then of course another techniques like characterize the structural and crystalline property. We have this Raman and XRD measurement, which can clearly show the formation of TiO2. So for example, if we are making some any other materials, means any materials are composite or hybrid structures or some different materials. So we have to first, you before the application, we have to know what is the structural property, what is the morphology, and what is the crystalline property, and then after that we can move for the application, because it should be like a process, our growth process should be like that. If in future if you want to repeat, at least you should know what is the growth parameter, then accordingly you can change, accordingly you prepare a material. It is not like randomly you make something one day and then another day we don't know. So that's then assuring the quality of the material is the one of the most parameters before the application. So for example, after that, we have grow this MOS2 on this TiO2 nanotube at 700 degrees Celsius. You can clearly see the change in the morphology. This MOS2 is coated outside of the TiO2 nanotube. Then again, we have performed this like Raman and then this X-ray photoelectronic spectroscopy. So basically, X-ray photoelectronic spectroscopy will tell you the what is the composition, what is the electronic structure of your system. So, for example, here we can clearly see this MO is there, sulfur is there, and then if you see there binding energy, because one of the parameters for the any material system to characterize this electronic property, the binding energy. So from binding energy, we can see when we have this pure moly, then their position will be different. And then if it is a composition or reaction, a compound formation, then it will shift the binding energy. So same thing happening here. We can have this pure metal of the different, but this MO3D and MO3D 5 by P to P is shifting. So it is showing the formation. It is not the pure moly. And then of course this sulfur is the same thing. So that's the reason it combining this formation of this MOS2, and then similarly for the TiO2 we have this TiE, and then oxygen, and then accordingly they have this TiO bond is also present there. It is showing the formation of the TiO2 as well. So of course we know the materials has been formed, we know the structural quality. Now we have to use this for the photoelectrochemical cell. So same thing, as I mentioned, it is different process required for the different 2D materials growth. So for example, here we again grow some this PTSC2. This is the one of the 2D materials. So again, here the same procedure we have. This like we have this titanium foil, then we use this electrochemical analysis. After that, we grow some platinum using this our sputtering system, and then after that, we again do the salinization. That's making this PTSA2, TI2 heterostructures and TI4. So again, we have done some of the SCM analysis. So also one of the technique during the SCM, okay, so when we have this bare TiO2, you have previously see it is not like this kind of, ring type of structure outside. But here you can see this during the, after the PTSC2, it is showing the ring type of structures. So during the SCM measurement, there is technique available that is called energy dispersive X-ray analysis, that is EDEX. So EDEX mapping is also possible. So it means we selected like a zoom area here, and then we put the all the combination of the materials. Like, okay, we know this is the TI, oxygen, platinum, and selenium. So here we can see the combination of TiO2, PTSC2, and then individual element we can clearly see. So for example, when we have this PTSC2, as I mentioned, that PTSC2 is coating outside the nanotube. So you can see the signal is coming only outside here, PT. Same thing, of course, this is the TiO2 and PTSC2. So this is selenium is the same as what of the platinum, because this is coming from the PTSC2. Interestingly, when we are coming to this TI or TiO2, here you can clearly see, of course, this material has been coated with the TiO2, like PTSC2 is coating, but also even below that one, because what of the space here or space is here, space is here. This is all also belong to titanium, because we use the titanium foil. So you can clearly see this titanium signal is larger compared to the platinum. So this is the one of the technique. Even people can see what kind of the elements present in the materials, and then accordingly you can see whether your materials or whatever your required materials has been formed or not. And of course, when we are going more details, like to really see the atomic scale images or to see the process really happening, that is, we have this technique that is called the transmission electron microscopy. So in the transmission electron microscopy, of course, we have the very thin structure of only few nanometer or few hundred nanometer structures we can measure. And after that, we can zoom even to the atomic scale image, even up to 5 nanometer, 10 nanometer area. And then from here, we can see what kind of crystal structure. So again, here we can see this is the TiO2, and then top of this, it is PTSU2 formation. So that is the one of the technique. Of course, it requires some dedicated, sample preparation is very difficult for the TiO2, and also of course it is destructive process. And same thing during the TiO2, this TEM measurement, we also done this elemental mapping. So this is again our PTSC2 coated TiO2. Here you can see this when we have the PT, of course PT is also here, and then PT is also here, and then selenium is there. But when we are coming to the titanium TiO2, we can just see, because this is the PT, this is the PT, but here there is no PT, because we are mapping the only titanium. So it means this is the reduced size compared to this one. The same thing for the oxygen. So it clearly mentioned or clearly showed, okay, whatever you have grown, it is covering outside the TiO2 nanotube. It is not going inside the nanotube. And then accordingly, even we can estimate that what is the thickness of the PTSC2. So of course, other approaches, we have done this Raman spectroscopy for structure analysis, then XRD. So all are showing the formation of the PTSC2 on the TiO2. And then in case of, again, XPS, we have done for the electronic property for PTSC2 on TiO2. And then it is clearly showing the formation of PTSC2. So we have this PEC measurement setup. So here we have this again 3 electrode cell. We use this electrolyte like Na2SO4, and then this is AgAgCl references. Then our photoelectrode system is this one, and then we have this platinum sheet that is for our counter electrode. So we have done for this first bare TiO2, for example. So when we are doing this bare TiO2, we can get this photocurrent density of 70 microampere per centimeter square. But when we are doing this, for example, after the coating of MOS2, then it is showing the enhance. It is almost 2 times enhanced compared to the only bare TiO2. And as I mentioned, of course, we have to see the stability test, and then after that, even we have done the different measurements. That is called this EIS Nyquist plot. That is showing inside the electrochemical cell what is the resistance. Basically, means it is measuring the impedance of the electrolyte plus electrode interfaces, and then accordingly you can see. So most of the things are, it depends on the what is the formation of arc, and whatever the arc of this EIS Nyquist plot is lower, it means showing the low interfacial charge transfer resistance. So it will help to produce more faster transfer rate between the electrode and electrolytes if you have the lower interfacial charge transfer resistance. So if we compare like MOS2 coated TiO2 have the low, so that's the reason we are getting the very high current density compared to the TiO2 and Ti. So of course, when we again going toward this, how what is happening and all other things, of course, we can see this energy band diagram. Then accordingly, it depends what is the band gap, and then how electron and hole pair are moving after the generating this electron hole pair in presence of the solar light. So of course, we can see MOS2 band gap is 1.7 electron volt, and TiO2 have this 3.2 electron volt. But also it depends what is this, conduction band edge position, balance band edge position, then accordingly your Fermi level will shift, then accordingly electron will move toward this from MOS2 to TiO2, and then TiO2 to TI foil, and then accordingly your efficiency will decrease or increase. It depends on the what is the band edge position. So as I mentioned, this band edge position also can be calculated using the XPS, that is X-ray photoelectronic spectroscopy. Another technique is UPS, that is ultraviolet photoelectronic spectroscopy. From there we can get the work function, and from XPS some calculation is there. We can get the what is the conduction band edge position, balance band edge position, and band gap we can know from our photoluminescence spectroscopy and this UV visual measurement. So that is the two three techniques to get this. What is the band gap? What is the conduction band position? What is the balance band position? And then we propose the different kind of the band diagram to support the finding of the results. So same thing we have done for this PTSC2 and this TiO2 structures, and here we can clearly see we are comparing with, like, even we have compared with this PTSC2, and then even without PTSC2 means PT and TiO2. So we can clearly see when we have this PT, then it is half of compared to the PTSC2. So that is the reason we have checked, and of course we have done the stability test, and we have found this PTSC2 have the more efficiency compared to this TiO2. So I will not go in more depth in this one. That this is just some glimpse that what we are doing here. And then of course EIS Nyquist plot is there, and then another is called this electrochemical active surface area. So that is the reason if you have this high electrochemical active surface area, then it means you have the more absorption of the light, more reaction is happening, then accordingly you are getting the more uh, current density. So in this case, of course, we have get for the PTSC2 coated TiO2 have the more surface area compared to the our only bare PT and TI2. So anyway, this is the again same. We have to explain how it is moving electron and hole pair, and then it will participating in the our um, current density. So I will just skip. We have taken some of the example because we have started with this titanium foil because it has been started this making the TiO2, and then of course people have done a lot of work. Then we have repeated, we established ourselves. Okay, already it is possible. We are able to enhance. Then we thought, why only to move toward this conventional materials? Use some kind of material that is even more easy way. So what we have done this here, we again use this titanium foil. So without doing any electrochemical analysis, we have done only formation of the TiSu2 with the single zone furnaces. So we have this selenium powder and then put the Ti foil at different heating temperature like 500, 450 degrees Celsius. And then after that, we get very good TiSu2 nano pyramid. Then of course we coated with some of the bismuth align materials. I will just show that one. So this is simply we heated titanium foil inside the selenium environment at 500 degrees Celsius, and we can clearly see the formation of the pyramid structures. Uh, I think before we have shown this, if we have this only titanium foil, it is the plain surface, it is not like the pyramid surface. And then again, after doing this elemental mapping, we can clearly see the titanium and selenium is there, so it is clearly showing the formation of TiSu2. So as we have done some XPS measurement, it is also showing the formation of the TiSu2. Then we have grow this bismuth cellulite film using this Manton sputting system. So that is the requirement. Of course, how we are making the different film. So I will not go in more details. So this is the again when we have this coating, we can see this platinum, this bismuth cellulite is only coating on the top of this TiSu2. So it is like again as mentioned, like when we have this fabricating the materials or fabricating in nanostructures, always we see what kind of the morphology is there, and again it is repeatable or not, stability is there or not. So of course when we have grown bismuth cellulite and TiSu2, again we can clearly see TiSu2 nanopyramids are there. So then we move toward this different characterization technique to assure that materials are hybrid structures has been formed. And then we have done this measurement of this electrochemical. Then here we can clearly see the when we have these hybrid structures, it depends on the what is the band gap and all other parameters. We are able to see the enhance in the photocurrent density compared to the only one material. So yeah. So I think I will just take maybe 10 more minutes. So one of the materials, of course, everybody know that is third nitride semiconductor. That is the one of the potential technological application materials. So when we see this, especially like energy band gap and this lattice constant, we can clearly see like different materials have the different lattice mismatches. So basically, you know, the strain and stress can happen when we are growing the film on the different substrates or different layers. But when we are growing the third nitride materials, there is no change in the lattice parameter, very low, like maybe 3.2 to 3.5 angstrom. So that's a there is minimum lattice mismatch. But you can see this band gap change is huge. Even you can tune the band gap from 0.7 electron volt to 6.2 electron volt, and gallium nitride is 3.4 electron volt. So one of the advantage, like even you can change the composition of indium, aluminum nitride, indium, gallium nitride, and then you can choose the whatever the light you want to use in the solar spectrum. Because as mentioned, when we wanted to use this uh, efficient way to get this our sun, or then we have to make it like a light can absorb all over the things. Means in the range from 200 to 1100. So one of the material is, of course, we can use these third nitride materials. So this is just example why we are interested or people are interested. Like of course, in future or even it is not possible to replace silicon, at least for few more years. But of course, we have the alternative in the future. It depends on the what is the application. So, for example, when we have the very good application, especially for the wide bandgap semiconductor materials, or direct bandgap, of course, gallium nitride is one of the materials. Then electron mobility, especially when you are using this high power devices. For high power devices, we want this breakdown field strength should be very high. So in case of silicon, it is 0.3, but in case of silicon carbide and gallium nitride, it is 3.5. So this is the one other reason people use this high electron mobility transistor using this third nitride materials. Anyway, so this is just to brief summary. And when we are going for the application of gallium nitride, you can name any of the solar materials or energy application devices, and it is there. For example, using gallium nitride, even you can make this LED devices. Most of the LED devices you can find on the traffic signal. It is made by this third nitride technology. And more interestingly, this three professor from Japan, Isamu Akasaki, Amano, and Suji Nakamura, they got this Nobel Prize in Physics for the invention of blue LED using this third nitride material only. Then, of course, you can use this laser diode, high electric mobility transistor, then solar blind UV photo detectors, then PC water splitting, solar energy application. As I previously shown, like it, when we are putting this indium or aluminum nitride, then accordingly it is covering all over the spectrum. So this is the materials. Of course, it can be used for different purposes. So again, it depends how we are going to use and why we are able to grow or not. So one of the limitations, just to make sensitize that uh, it is not possible to get the gallium nitride wafer like silicon wafer, because when people they started even 1997 to grow crystal growth of this gallium nitride, but they are only able to grow 6 to 10 size in 60 to 100 hours, even having 1200 uh, degrees Celsius before the growth. Then people thought, okay, it is not possible. That's an gallium nitride technique. It took a lot of time before the commercialization of these LED devices due to the non-availability of the large wafer like silicon. But of course, there is different way how we can use. Of course, we can grow the gallium nitride film on the different substrates. That is we call the epitaxial gallium nitride growth technique they have. And for example, we have the different techniques as well, and it depends what you want. You want a very high growth rate, or you want the control over monolayer film. Monolayer means even you can grow 1 nanometer, 2 nanometer film. So that is the, if you want to grow high purity and want to 2 nanometer film, that is we have this MOC, MBE system. That's molecular beam epitaxy. If you have this high growth rate, then of course you can use this HBP. So here you don't have the control, but if you want thicker, like 400, 500 micrometer thicker film, then you use the HBP, because this MBE will take maybe 2 days to grow the 400, 500 micrometers. So that's reason it depends on the what is the application. Then accordingly people select the techniques, and then again select the substrates, because substrate is also important. Whether you want sapphire, silicon carbide, it depends on the what is the application. So here, of course, we have this. I will not go in more details here. So basically, here we have at NPL we have this laser MBE technique, and that is one of the technique that, especially when we have this talking about this vacuum. This is we call the ultra high vacuum system. That is base pressure is 2 into 10 minus 10 tar. So it means whatever the atmospheric pressure is like 760 tar, we have 10 minus 10 tar. So of course we have the control over this different um, pumps and all other things, because we don't want any contamination and any impurity of the oxygen or anything inside the system when we are doing the gallium nitride. So of course that's reason we need very uh, high environment, means ultra high vacuum environment. So of course, every system comes even with the in situ characterization technique. So one of the in situ characterization technique is read pattern, that is reflexive high energy electron diffraction. So even during the growth, we can see, for example, when we have this gallium nitride template, we can clearly see the formation of only this sticky pattern. But when we are growing the film, we can this is spotty pattern that is clearly showing the formation of our uh, gallium nitride growth is happening. So this is the one of the technique even you can know before taking out the sample. So this is some of the example. We grow some nanostructures. I will not come. So again, in this case, we started with this growing some nanorods of this gallium nitride and titanium foils. Then it is easily we can see clearly formation of this different nanorods. So I think yeah. Then we use for this water splitting process. Then again we have with this different gallium nitride nanoflowers. Then here again we have quoted this one of the more studied material that is called the RGO, reduced graphene oxide. We after the growth of the gallium nitride using the MV technique, we use this RGO coating, and then again we have cation. So of course, when we have this RGO, we can clearly see the formation of means getting the more broader range. So that's reason it is going to absorb more light. And then we have done this FESCM, XPS, and all other measurement to rely that okay, this is our system is perfect. Materials has been grown, and then we studied this PEC water splitting again. And from here we can clearly see when we have this gallium nitride only, the current density is, for example, 60. But when we have this RGO, it is showing around 120 or 130, 115. So that's reason it is showing this hybrid structure is always helping. So I think, and then of course we have done this EIS Nyquist plot and all other stability tests. And then again, as I mentioned, this is a band diagram. We have calculated all these positions like EC, and then this gallium nitride, all other things using this XPS technique, and then band gap from our different PL system. So then we have fabricated this mechanism is there. So I think I just want to conclude that I just try to briefly discuss the importance of hydrogen, why we are interested in the hydrogen energy, and then what is the procedure to get this hydrogen energy fuel cell. That is the one of the technique, that is the PEC water splitting system. And then why we are need of doing these flexible devices for roll to roll fabrication, that is also has been discussed. And I have taken some of the examples of growth of these different materials on TiO2 and TI foil, and also some third nitride materials for their applications in case of water splitting. And then of course we have chosen some other material, that is the third nitride semiconductor, even on the flexible metal foil. We saw that the combination of hybrid structure is the promising material to get the more energy density, current density. So that is the one of the way that we can increase the efficiency of our hydrogen fuel cells in the future. So of course, it is not like only my work and only I can do, because this is the research. We collaborators are one of the most important factor, means how you collaborating and what are the system we have. So of course, I would like to thank our collaborators, Dr. Senthil Kumar, Dr. B.N. Singh, Dr. A. Kumar, and from outside NPL, Professor Somnath Rai from IIT Madras, Pujay Yadav from SSPR, Dr. Ganesan from BITS Pilani, and Dr. Sarma from NIT Hamirpur. And I would like to acknowledge my director, CSI NPL, Professor Venugopal Achanta, our HOD, and this most of the work is done by my past and current student, Mr. Bhim Singh, Dr. Ramesh, Dr. Sudhanshu, Vishnu, Rahul, and of course funding from this our SERV DST, and then CSR first funding. So if you have any question, I will be happy to answer. Sorry, I have a meeting, so that's it. I try to complete within 1 hour 20 minutes. Yeah.
Thank you, sir, for enlightening us with this informative session. Participants, if you have any query, you can ask. Participants, if you have any query, you can ask. Okay, sir. I think there is no query from participants. So we would like to extend our sincere gratitude to Dr. Sunil Singh Kushwaha, sir, for his outstanding lecture today. Your deep knowledge and passion for the subject were evident, and your insights on various growth and characterization techniques for materials and how hydrogen can play a critical role in the transition to sustainable energy were truly enlightening. Thank you once again for your time and expertise. Thank you, sir.
Okay. Yeah. Thank you. Thank you all. Yeah.
Okay,
Okay.
sir.
Yeah. Okay.
Now we
Thank
can,
you.
thank you, sir. Participants, we can leave now.